Where I'm going is we're going to be talking about a number of these things, but I think it's appropriate at this point to give a little context of exactly what we're going to be talking about and what we're not. We're going to be talking about electronic computer logic, not mechanical. Now, in the past, there have been attempts to do mechanical computers. This is one. It's actually a model that is in the British Museum of a device built by a man named Charles Babbage. The second thing is we're going to be talking about digital computers, not analog computers. Now, an analog computer is shown here. This is actually a computer that was used by the U.S. Navy during World War II and for some time after it. It's since been replaced with digital computers, but it's the Torpedo data computer. Basically, this was a series of gears and motors and other things that helped the skipper of a submarine calculate the firing position for a torpedo based on the course and speed readings that they got through the periscope. When you talk about computer logic, there are two kinds of computer logic. We're going to focus mostly on combinational logic. We may later do a second series on sequential logic. The difference is combinational logic, you apply the inputs and then you wait an appropriate amount of time. These days that's nanoseconds, but you wait a little bit of time for everything to settle down, and then you read the output. When we talk about logic circuits, that's the same as saying a switching circuit. The reason is you can use switches, you can use relays, you can use diodes, you can also use transistors. When transistors started being used, the first type of transistor logic was called resistor transistor logic, then diode transistor logic, then transistor logic, later CMOS, or complementary metal oxide semiconductors, that's a mouthful, Schottky, ECL, that stands for emitter coupled logic, and pretty much the present day is advanced CMOS T, which stands for TTL. In other words, it's an advanced CMOS logic with TTL levels. Now, why do I go through all of this? Well, if you need to do some research on the web or in a book, you probably want to know how to spell some of these terms and what some of these terms might mean. When we talk about gates, we just mean functions or operators. For example, the AND, the OR, the NOT, the NAND, the NOR, the XOR. We'll talk about these a little bit, but quite frankly, you don't have to learn these. If you get out a good data book on, say, a line of TTL or CMOS or advanced CMOS, they'll tell you what these functions are and how they work. So you don't really need to memorize a lot of this, but it is a good idea to have a concept of what is going on. And one of those concepts, and this is the last algebraic lesson, there is a fellow named De Morgan who developed a law that said if you take A or B and invert it, what you get is the same as inverting A ANDed with inverting B. The reason that I point this out is because this is the basis of what is called Boolean algebra, or the algebra of logic. We're also going to talk a little bit about logic simplification, but one reason I don't emphasize this very much is There is a method called the Quine-Mccluskey method, and once again, I only give you this so if you want to look it up, if you're curious, this is how it's spelled. This method has been implemented in computers today, and because it's been implemented in computers, it's a lot faster and easier to use than trying to do it yourself. There is a method that is a little more intuitive based on a map by a guy by the name of Karnaugh. We'll look at that, but basically logic simplification today is like well, it's all done on a computer. It's people don't do spreadsheets by hand anymore, and they certainly don't do logic simplification. By way of introduction to why you might want to use a Karnaugh map for some things, these are some basic logic gates that you'll find in a logic catalog, TI or Fairchild or whoever. And this is usually the way they are written. If you have a straight line on the front of the gate with inputs, and I'm only showing 2 here, there could be 3, 4, I think there are some that have as many as 15 or 16 inputs, but the output is described in what is called Boolean Algebra as A dot B. The dot means and that's why it's called an AND gate. If the front is curved, then it's A or B, and in this case it's not plus, this is OR in a logical function, and that's why it's called an OR gate. There is also a gate called a buffer gate in which the signal is just repeated. Notice that this gate does not have anything on its output, nor do any of these up here. If you have the outputs inverted, you get these 3 gates. A, B with a circle. That means that A and B, just like the one above, but with the output inverted. This is called a NAND gate, or a not AND gate. Similarly, if the front is curved so that it's an OR gate but with an inverted output, then what you get is A or B inverted. That's a NOR gate. If you have a buffer with its output inverted, then what you get is the inverse of what you put in. You put in A, you get not A, or an inverter. One of the things that people have found useful in doing logic is a thing called a Karnaugh Map. And you might see this in some old logic simplification diagrams. How useful is it? Well, let's take a look at a situation where we might use a Karnaugh map. Now, here I've written a string of terms. Once again, this is the sum of products form. The first product is A, B, not C, not D. The second, A, not B, not C, not D. The third, A, B, not C, D. The fourth, A, not B, not C, D. But what a Karnaugh map allows you to do is to conceptualize where these terms interrelate. Let's see if we can do that. What I've now done is written each of these terms, each of these products in the Karnaugh map. There are 4 terms, so there are 4 ones. Once you have written the terms, you can then simplify what you've got by grouping similar terms. Because these all 4 are adjacent, what we can do is group all of them. Now let's write down what those 4 terms are, or maybe more appropriately, what are the values of A, B, C, and D that are common to everything in that square. Well, if we look, A is always a 1 in this square. So we can write down A. B changes. C stays the same, but it's inverted. So we write down not C. D changes. So we don't write that down. What we have shown is that this long, complicated equation at the bottom simplifies to A not C. You have passed through the really tough part of the course, and from here on, I hope you'll find it's mostly just fun. So stay tuned and have a nice day.